Everyone debating the simulation hypothesis asks, is it possible? Nobody asks the sharper question, what does quantum mechanics actually demand from the simulator? Because the moment you go quantum, and you have to go quantum, a classical simulation was never going to work. You inherit the full weight of Hilbert space, and Hilbert space is not forgiving. For our universe's particles, the dimensional math reaches numbers so large that writing them down is physically meaningless. That's not a processing bottleneck. That's a fundamental law baked into the structure of quantum reality itself. This video is that question, finally asked properly. By the end of this, you won't just doubt the simulation, you'll understand exactly why quantum mechanics is both its greatest hope and its final execution. And the answer doesn't leave room for ambiguity. Not for quantum computers, not for any computer, not ever. If this is a simulation, the system isn't going to crash from rendering 8 billion human minds. It's going to crash the second it tries to calculate quantum mechanics. The quantum world requires a mathematical space that inflates so violently, a classical computer literally cannot hold the data. It's not a processing lag, it's a hard physical limit. So, classical computers are out. But simulation theorists have one final lifeline they love to pull. Feynman himself proposed quantum computation precisely because quantum systems simulate other quantum systems without exponential overhead. Give the simulator a quantum computer, and your scaling argument evaporates. This is the strongest counterargument available. It deserves a precise answer, and it gets two. First, the resource problem does not disappear. It transforms. To quantum simulate a system of n particles, you need a quantum computer with at least n qubits, particles of physical matter maintained in coherent quantum states. To simulate our universe's roughly 10 to the power of 80 particles, you need a machine containing at least 10 to the power of 80 coherent qubits. That machine is itself a physical system, occupying space, consuming energy, obeying whatever thermodynamic laws govern the simulator's reality. It must be at least as large and complex as the universe it models. At that point, you haven't built a simulation, you have built another universe. The word simulation has become a label with no content. But the deeper wall is not physical, it is mathematical, and it applies to every computer that could ever exist, classical, quantum, or otherwise, under any conceivable laws of physics. In 1936, Alan Turing proved that no computational system can universally predict whether an arbitrary computation will finish or run forever. This is the halting problem, and it is not a technological limitation. It is a theorem, a proven, permanent boundary on what computation can determine about computation. Now apply this to simulation. Our universe contains computers, biological ones like human brains, and increasingly artificial ones. A faithful simulation must reproduce the outputs of those computers exactly. But Turing's proof tells us that some of those outputs are undecidable in advance. The simulator cannot shortcut them. It cannot predict what a computing being inside the simulation will calculate next without actually executing the full computation step by step in real time. Every abbreviation risks producing a simulated mathematician who proves false theorems, a simulated physicist whose experiments contradict the very laws the simulation is supposed to encode. And here, the problem recurses. If a civilization inside the simulation builds its own simulations, which we, right now, are already doing, the simulator must simulate the simulation. And if that inner simulation contains beings who build further simulations, each layer demands full computational fidelity for every layer beneath it. The cost does not merely grow, it nests, it compounds. And at every level, the halting problem guarantees that no layer can be compressed without risking logical contradiction.
This is not about processing power or cleverness. It is about what computation itself can and cannot do. Turing didn't prove that today's computers can't solve this problem. He proved that no possible computation can. Not on silicon, not on qubits, not on substrates from a universe with laws we have never imagined. The proof is mathematical. It is substrate independent. It is permanent. So the simulation hypothesis now faces a trilemma of its own, one far less comfortable than Bostrom's. Either the simulation doesn't faithfully reproduce computation, in which case it isn't simulating minds and consciousness is an illusion inside it, or it does reproduce computation faithfully, in which case it requires a machine at least as complex as reality and the word simulation means nothing, or it tries to shortcut the computation, in which case Turing's theorem guarantees it will eventually produce a logical contradiction, a glitch not in the rendering but in the mathematics of the simulated universe itself. Pick your option. None of them lead to "we are probably simulated." Let's lay out what the evidence actually establishes. The classical computational requirements for simulating a universe are enormous. Exabytes of storage, 10 to the power of 22 operations per second, energy budgets governed by Landauer's principle, but not theoretically insurmountable for a sufficiently advanced civilization. That layer of the simulation argument, while strained, survives contact with physics. The empirical tests do not rescue it. No experiment has detected lattice-scale Lorentz violations. No cosmic ray spectrum reveals grid-aligned energy cutoffs. No structure in the cosmic microwave background betrays a pseudo-random number generator. Every measurement we have is consistent with a universe that is continuous, isotropic, and unsimulated. But it is the quantum complexity argument that closes the door and welds it shut.
The Hilbert space required to describe a quantum system scales as 2 to the power of n, where n is the number of particles. For just 300 particles, that yields approximately 10 to the power of 90 dimensions, 10 billion times more than the total number of atoms in the observable universe. For the universe's actual 10 to the power of 80 particles, the dimensionality becomes 2 to the power of 10 to the power of 80, a number so vast that no notation in mathematics makes it feel small. This is not an engineering bottleneck awaiting better hardware. It is a scaling law, a boundary built into the structure of computation itself. No classical computer, not one constructed from every atom in every galaxy we can observe, could store the quantum state of a single gram of matter, let alone simulate its evolution forward in time. And here is the deepest consequence. The only system capable of computing the quantum behavior of the universe with perfect fidelity is the universe itself. Every entangled pair, every superposition, every quantum field interaction is a calculation executing in real time at a density of information processing that no external machine could replicate. Reality is not running on something. Reality is the computation. Any machine built to simulate it would need to be larger than the universe it attempts to model, at which point you are no longer describing a simulation. You are just describing another universe. What we are part of is not a program. It is a self-computing quantum system whose full description exceeds the capacity of any computer that could ever be constructed within it. That is not less remarkable than being a simulation. It is incomparably more so. The upshot, if the future civilization is running such sims, either they have unfathomable compute or they limit the simulation in clever ways: coarse-grained physics, selective fidelity, or partial realism. That gives us a clue. If simulations are being run, they're probably not perfect atom-for-atom recreations of entire planets. They're optimized. Which brings us to a powerful critique: Occam's razor. The simulation hypothesis often flips Occam on its head.
Instead of positing a simple, elegant underlying reality, it posits a more complex infrastructure behind everything. Why not accept the simpler explanation that reality is real, unless there's good reason to posit a simulator? Proponents counter that the simplest statistical expectation given multiple ancestor simulation instances leads to the simulation being more likely, but that argument depends on debated priors. Bayesian inference is great, but garbage in yields garbage out.
What about consciousness as evidence? Some argue that subjective experience feels real, and that such realism indicates a base reality. But that's a philosophical move. Your experience doesn't give a meta-ontological certificate. If you're simulated, you'd still have vivid experiences. That's the creep. The simulation hypothesis is consistent with virtually any observation you make inside the simulation, which makes falsification tough. So what is the best scientific stance? Skeptical, curious, and cautious. Simulation theory is a serious philosophical and occasionally scientific conversation starter. It has motivated, clever empirical proposals, which is good. The correct scientific attitude is to test the testable and admit the limits of the rest. If future experiments found Lorentz violations implying a lattice scale, or if cosmic ray spectra showed telltale anisotropies tied to a grid, that would be revolutionary. Until then, the hypothesis sits in a gray zone, interesting enough to discuss, but not yet evidence-backed.
Now, every claim I have made in this video is mathematically specific and, in principle, falsifiable. If you can resolve the exponential scaling problem, I want to see your argument. I have opened the Community tab for exactly this purpose. Subscribe to the Cosmic Codex for more arguments built on evidence rather than assumption. And the next time someone tells you we are living in a simulation, ask them one question. How do you plan to classically simulate a Hilbert space of dimension 2 to the power of 10 to the power of 80? Then watch them change the subject. Until next time, demand the math.